The statement is if sequence Sn is a sequence of non-negative numbers and limit of Sn is L as n tends to infinity, then the limit will be greater than or equal to 0. Yeah, definitely it is true. It is sequence of non-negative numbers, that means positive numbers and 0. Then the limit of the sequence can be either 0 or greater than 0. So the proof, suppose what happens if the limit is not greater or equal 0? That means we suppose on contrary the limit is negative. Then what will happen? Then for epsilon is positive and L is negative. So if I consider L by 2, so it will be negative. So I consider minus of L by 2, which is to be positive. And since limit of Sn as n tends to infinity is L, therefore by definition of limit of sequence for every epsilon which is we have chosen to be minus L by 2 and is greater than 0, there exists a positive integer n such that equation star holds. That means Sn minus its limit is less than epsilon for all n greater or equal n. Right? The limit exists and it is L, which is we have considered it is to be negative. So that is Sn minus L is less than epsilon. Epsilon is what we have chosen it to be minus L by 2. So that is in particular it is true for all n greater equal large n. So in particular we consider for equal to the large n, Sn minus L is less than minus L by 2. Right? That means it will be minus of minus L by 2, that means L by 2 less than Sn minus L is less than minus of L by 2. So what we get? That is, it means from these two terms Sn will be less than minus L by 2 plus L. So it is less than L by 2. So if the limit of the sequence is L, so is it true that for large n the sequence will be less than L by 2? Definitely not. And it is sequence of non-negative real numbers. So it says that the nth term is less than L by 2. That means negative? No, definitely not. Since L is less than 0, L by 2 is less than 0 implies the nth term of the sequence is negative and is a contradiction. To the sequence Sn is a sequence of non-negative numbers. So L cannot be negative. So L has to be positive or greater than 0. Right? So let us see example. If Sn is a sequence of real numbers if Sn is less equal capital M when n is a positive integer and limit of Sn is L, then this L is also less equal capital M. Okay. So the solution, what we have given, Sn is sequence of real numbers. It is bounded by some real number M. Then if limit of sequence is L, then definitely this limit is less equal the upper bound of the sequence. Right? So it is given that sequence Sn is bounded by M for all positive integer n. So that means the sequence M minus Sn is positive for all integers or positive integers n. So it means what? So that means it is M minus Sn is also a sequence of non-negative numbers. Sequence of non-negative numbers. Therefore, by previous theorem, the limit of the sequence M minus Sn should be greater equal 0. That means L has to be greater equal 0. Right? That means that is M minus limit of Sn as n tends to infinity has to be greater equal 0. That is M minus L. It is the limit is L. It is given is greater equal 0 or L is less equal M, and it is what we wish to show. The next example, number 2, it is find a positive integer n such that the absolute value of 2n upon n plus 3 minus 2, it should be less than 1 by 5 and it should be true for all n greater equal n. Right? So solution, you have to find the largest value of n satisfying this. We have to find value of large n so that the least value of n satisfy this thing. Right? So solution, consider it should hold 2n upon n plus 3 minus 2 is less than 1 by 5 for a natural number or positive integer n. So simplify this thing. It means it is 2n minus 6 divided by n plus 3 less than 1 by 5 and n is positive integer. So it means by simplifying and taking absolute value, it is 6 upon n plus 3 less than 1 by 5 when n is positive integer. Or then now simplify this thing, 30 is less than n plus 3 when n is positive integer. So n should be greater than 27. So this thing will satisfy if n is greater than 27. Right? So what the large value of large n or smallest value of n or value of large n satisfying this thing or this equation, this inequality or the equation star will be greater than 27. Therefore, so if we choose a value of large n or least value of small n satisfying this equation, so if we choose large n such that it should be greater than 27, then our equation 1 must hold. So the value of capital N satisfying this is at least 28. That means greater than 27. Right? Now the next example show the limit of 2n upon n plus 3 as n tends to infinity is 2. So how to show? So we have to use the definition of limit of sequence, and by this definition we have to find the value of largest n or large n. That means we have to find the least value of small n satisfying the definition. That means it is enough to show that for every epsilon greater than 0 there is or there exists a positive integer n such that the definition of limit of sequence should be satisfied, such that 2n upon n plus 3 minus 2, the difference should be less than epsilon for every given epsilon greater than 0, and it should be true for all n greater equal the large n. That means we have to find the value of this n. Right? So this gives what it gives, 2n upon n plus 3 minus 2. So it is 2n minus 2n minus 6 upon n plus 3 less than epsilon. It should be true for all n greater equal n. That means simplify this thing, it is 6 upon n plus 3 less than epsilon. It should be true for all n greater equal n. Right? That is, it means 6 upon epsilon should be less than n plus 3 for all n greater equal capital N. It means n should be greater than 6 upon epsilon minus 3. So what the value of capital N I should choose? So the least value satisfying this is greater than this. Therefore, if we choose a positive integer n to be at least greater than 6 by epsilon minus 3, then what will happen? This difference is less than epsilon for all n greater equal capital N. That is, we can say that limit of 2n upon n plus 3 as n tends to infinity is 2. So one example for homework is there. Find positive integer n such that 1 upon square root of n plus 1 is less than 0.03, and it should be true for all n greater equal n. So try to find out. The next example for homework also. It is limit of 1 upon square root n plus 1 is 0. Try to show this. Instead of homework, take it as an assignment. Assignment 2. This is example 1, example 2, example 3. Prove that sequence has a limit or does not have a limit. The first sequence is n square upon n plus 5, and the hint is that it does not have a limit. So try to show how to show. Next, the sequence is 3n upon n plus 7 times n raised to half, and the answer is, hint is that limit is 3, and try to show you how to find the value of the value of n, so that the definition of sequence of limit of sequence is satisfied. And the next one is (3n upon n plus 7n square), and the hint is that has no limit. So try yourself, and the answers or hint is given with this assignment. The next example. The assignment is over, and the next example is the sequence 10 raised to 7 upon n has a limit 0. So how to show? So for every epsilon greater than 0, we find positive integer n such that the absolute value of 10 raised to 7 upon n minus 0 is less than epsilon, and it should be true for all n greater or equal n. So that means 10 raised to 7 upon n should be less than epsilon for all n greater or equal n. It means n should be greater than 10 raised to 7 upon epsilon. It should be true for all n greater or equal n. So if we choose positive integer n to be greater than 10 raised to 7 upon epsilon, then the sequence Sn minus 0 is less than epsilon. It should be true for all n greater or equal n. That is, limit of 10 raised to 7 upon n as n tends to infinity is 0. Okay. The next thing is, I think it can be done as a homework. The sequence n upon 10 raised to 7 has no limit. So try to show by contradiction. On contrary, suppose it has limit and some contradiction will be there. Similarly, homework. Next, the sequence n minus 1 by n also has no limit. Then the next example, if sequence Sn is 5 raised to n upon n factorial, then show its limit is 0. So the solution is S1, the first term of the sequence will be 5 upon 1 factorial, that means 5. S2, the second term will be 5 square upon 2 factorial. And the third term will be 5 cube upon 3 factorial. The fourth term will be 5 raised to 4 upon 4 factorial. The fifth term is 5 raised to 5 upon 5 factorial. Right? It is the fifth term. The sixth term is 5 raised to 6 upon 6 factorial. So can I do something with this? So I can write it as 5 raised to 5 upon 5 factorial into 5 by 5. Into 5 by 6. Is that right? Five by 6, yes. Then S7 is 5 raised to 7 upon 7 factorial. So I can write it as 5 raised to 5 upon 5 factorial into 5 into 5 divided by 6 into 7. So it can be less equal, definitely less equal. 5 raised to 5 upon 5 factorial into 5 by 5 upon 5 into 7. So it can be less equal 5 raised to 5 upon 5 factorial into 5 by 7. It is equal to 5 by 7. Okay. And this thing now I can change. It can be less equal 5 raised to 5 upon 5 factorial into 5 by, no, it is equal to, yeah, no problem. Then S8, it is 5 raised to 8 upon 8 factorial. So I can write it as 5 raised to 5 upon 5 factorial into 5 into 5 into 5 upon 6 into 7 into 8. So you can write it as, this thing will be less equal 5 raised to 5 upon 5 factorial into 5 into 5 into 5 upon 5 into 5 into 8. So this thing will be 5 raised to 5 upon 5 factorial into 5 by 8. Right. So in general, what we can say about Sn? Definitely it will be less equal 5 raised to 5 upon 5 factorial into, for S6 it is equal to 5 by 6, for S7 it is less than 5, this factor into 5 by 7, for S8 it is less than, so it is upon into 5 by n, and it is true for all n greater equal 6. Before S6 the equality is there. So thus for a given epsilon greater than 0, there exists positive integer n such that this Sn is less than epsilon for all n greater equal n. That is 5 raised to 5 upon 5 factorial into 5 by n is less than epsilon for all n greater equal n. That is, what n should be chosen? So n should be greater than 5 raised to 5 upon 5 factorial into 5 upon epsilon. And then, so what value of large n? The least value of small n is large n to be chosen, so that this star should be true. So thus, if we choose positive integer n to be at least greater than 5 raised to 5 upon 5 factorial into 5 upon epsilon, then what we have? Star holds. So that is, limit of 5 raised to n upon n factorial is 0.